Hi, this is Professor Fernandez, and this is video 1 in lesson 18. We're talking here about indefinite integrals, and we are going to calculate 4 of these across these examples from Calculus Simplified. So first thing I want to do is zoom in to the first example, and then see what we're going to need to use to calculate that one. So this says example 5.9, calculate integral of x squared dx. So this may be new notation. It certainly is for this part for us in the course. So I'm going to scroll to the right here and just remind you what this notation means. That's down here. So this is about the indefinite integral. So what's the definition here? This is from Calculus Simplified. Suppose capital F is an antiderivative of little f. So that capital F prime equals little f. We then write the integral of little f of x dx is capital F of x plus c. So the left-hand side is called the indefinite integral of little f. So we'll see this right now in the example. It's really great to illustrate this through an example. Helps it sink in. So if I am looking at this integral of x squared dx, so what am I trying to find? I'm trying to find a function, capital F, which differentiates f prime of x to this x squared, the integrand, little f of x. And there are lots of ways that you can try to do this. You can certainly try to do it in trial and error fashion. That's something we did in the previous previous lesson, or you can try to be a bit more systematic. So I'm going to scroll out here, zoom out, and then scroll to the right. This is what you get if you try to do things in a more systematic fashion, at least for power functions. So this is the integral version of the power rule. So what does it say? It says if I want to find the integral of x to the n, where n is any real number that's not equal to -1. That's a special case we'll talk about later. Then the answer is you add 1 to the exponent, that's the n plus 1, and then you divide by the result. And then the plus c is always there for the same reasons we talked about in the book. So I refer you to the chapter 5 and around these theorems for a discussion of what this plus c means and why it's there. Okay, so we're going to use this integral version of the power rule. So the way to remember it is if you're integrating x to the n, you add 1 to the exponent, divide by the result. Should kind of remind you of the power rule for derivatives, where you bring down the exponent and you subtract 1 from the exponent. So in terms of x squared here, what am I looking for? So if I use the integral version of the power rule, first I have to identify the exponent, that's 2. So I'm going to add 1, 2 plus 1, and then I'm going to divide by the result, 2 plus 1, and then plus c, right? So that gives me x cubed over 3 plus c. And it's always good to check your work when you're calculating these things. So does this condition hold, right? Is the function that we just got, which is, this is the capital F of x here, x cubed over 3, does it differentiate to x squared? Well, let's try it out. This is where it pays to remember all the work we did in chapter 4 of this book with the differentiation rules. This is a power function, so if I find its derivative, I would be using the power rule, which would give me 3x squared. And then also the fact that, multiple of the function, when you differentiate that product, you get a multiple of the derivative. So I divide by 3, and I would get back the x squared that I had to begin with. So that's the integrand. So I'm going to erase all of this and keep the most important part, which is just the actual calculation of the integral. So there we go. So I'll slide this over. So integral of x squared dx is x cubed over 3 plus c. Okay, so let's apply the same thing over here. This example, notice that we now have a definite integral versus an indefinite integral. So there are various ways you can do this. The way we've been doing it in the course is through the evaluation theorem. So I'm going to scroll down, remind you what that one says. So I covered the details of the evaluation theorem in video 17.3. So if you want to go there for a more detailed review, please do so. But at this point, let me just read what the theorem says, right? So suppose the integrand function is continuous on the interval we are integrating over, and you have found an antiderivative, right? We will have done that already for the example we're about to do because it's x squared that we just did. Then the integral of little f of x dx from a to b is just evaluating the antiderivative capital F at a and b and then subtracting the result. So that really is the evaluation theorem, so aptly named. Okay, let's go back here. and apply that, notice that the integrand, x squared, is the same as the one we just did, right? So if I zoom out here, the only difference between these two integrals is that this is an indefinite integral, this one, and this one is a definite integral. So integral from 0 to 1 of x squared dx. We have already found an antiderivative of this function. It is x cubed over 3. And then just in terms of notation, a lot of times you'll see this bracket used. And then the limits of integration put there. Just as a reminder of what the quote a and little b values are for capital F of b minus capital F of a. And then now what you do is you substitute this number into here, 1 cubed over 3 minus, substitute that one, 0 cubed over 3, and then you just do the arithmetic. This is 1/3 minus 0 gives you 1/3. So that is the value for this definite integral. So you can see that evaluating definite integrals using the evaluation theorem is a two-step process, right? Number one is this. This is number one. Find the antiderivative, right? Find capital F of x. And then number two is this step. This is the capital F of b minus capital F of a, and simplifies to whatever numerical value you get. Okay, so let's keep going here. Example 5.11. This one again is an indefinite integral. There are no limits of integration. There are no numbers over here, down here, and down here. So we are not going to use the evaluation theorem, but we are going to use the integral version of the power rule that we did in the first example. To do that, I have to rewrite the integrand, 1 over x squared, as a power function. So remember that we do that by writing it as x to the minus 2. Because negative exponents, again, reciprocate whatever they are the exponents of, right? So that would get us back to 1 over x squared where we started. Okay, so now we see this as a version of x to the n as a power function, and the integral version of the power rule tells us to do this. So in this case, if we compare, we see that n is negative 2. So using our power rule integral version, we add 1 and then divide by the result, and then plus c. So if we simplify here, we have x to the negative 2 plus 1, that's x to the minus 1, over negative 2 plus 1, minus 1, plus c. This is the answer. So if you want to keep it in this form, that's okay. Or you could simplify it to minus 1 over x plus c. So that would be the indefinite integral. I won't do it here, but I'll encourage you, once again, as a practice of your derivative rules, and also to make sure you apply this integral version of the power rule correctly, you might want to differentiate this. Make sure that you get x to the minus 2, right? That's a good check for your work. Okay, I'll scroll over here to do the last example in this set. Same deal here. We're doing an indefinite integral. This time we have same kind of need to convert this to a power function. So how do we do that? Well, x square root of x is x to the 1/2. And that's a little simpler conversion to a power function. We know that now the n is 1/2. So to use the integral version of the power rule, once again, I just add 1 to the exponent, divide by the result, and then plus c. And from here, it's just algebra. So 1 plus 1/2 is 3/2, and 1 plus 1/2 is 3/2. Again, this is the answer, but I'm dividing by 3/2. That's the same thing as multiplying by 2/3. So that gets me to this cleaner version of the answer. So I'm going to zoom out here and just run through a few quick little takeaways. So we did 3 things here in this video that we applied. The first one was to talk about the difference between indefinite and definite integrals, right? So the indefinite integral, you're looking for the antiderivative, the function that when you differentiate it gives you back the integrand. So if I take the derivative of x cubed over 3, I get back this integrand. If I take the derivative of this function, I get back x to the 1/2, right? So that's what indefinite integrals do. Definite integrals, as we've seen from video 17.3, they yield numbers, right? So you're looking for a number that represents the area under the curve y equals x squared. Later on, we'll talk about net signed area, but so far in the course, we've only been considering functions that are integrating, definitely, functions that are positive. So that was the next thing we talked about. And then the integral version of the power rule is what gives us our formula for how to actually calculate the antiderivatives of functions that are power functions, x to the n. And the rule is fairly simple. So as long as you identify the power, right, which may require rewriting the function in different ways, you add 1, divide by the result, and that's your antiderivative.